I know that this topic of pointwise versus uniform convergence is difficult here. So let me iterate a little bit and let me explain once again and with different arguments why this cannot be uniform convergence in this example here. And to do so, let's look at the matrix perspective. So on the one hand, we have the operator A, that was the identity, taking the sequence to just the same sequence again. And on the other side, we have the operators AN that also take the sequence and truncate it after the first n entries, filling the rest with zeros. So if you want to identify these infinite vectors with column vectors, then you could write down AN and A in terms of matrices. And not surprisingly, you would get that A is the infinite identity matrix, whereas AN corresponds to something slightly different. So here only on the first n components you can see the identity matrix, and then the rest of the main diagonal is just deleting everything. Now as n goes to infinity, this truncation point is moving out towards this corner here, which of course is infinitely far away. And you can see that this blue main diagonal is convergent pointwise to that red diagonal. So sooner or later, at every position where there used to be a 0, it's going to be a 1. You just have to wait long enough until n has passed this position. But the convergence is not uniform, because when you look at the norm of the difference, then you see the norm of that matrix, and the norm of a diagonal matrix is given by the supremum norm, by the infinity norm of that diagonal. So you take absolute values, then the supremum, and that's your norm, which in this case gives you 1, and that does not go to 0 as n goes to infinity. This rule about the matrix norm or operator norm of a diagonal matrix it's going to be checked in problem 14 on our third exercise sheet. So if you want, you can do that now. I'll upload it. So it remains to check that via the definition in this example we have strong, that is pointwise convergence. Okay, so this time you start by fixing any vector x, and then instead of looking at the norm of the difference of your operators, you look at the norm of the difference of whatever your operators are doing with this x. Okay, and norm means 2 norm. And then we just copy from here, which gives you the norm of this vector. And if you compute that using the definition of the 2 norm, you get this. And actually maybe here it helps to write this using the summation sign. But then this goes to 0 as n goes to infinity. And here is the argument. We know that x is an element of capital X, which is little L2. But that means this series converges. But when we say that the series converges, then since analysis 1, what we mean is that the sequence of truncated summations converges, and it converges to that number here as n goes to infinity. But that of course means that the difference between these two goes to 0, which of course explains our argument here. So I mean you could say that this is just the remainder of a convergent sequence, and that remainder goes to 0, of course. So yes, in our example we have strong convergence or pointwise convergence, whatever you prefer. And at the same time, this example shows that this new convergence is weak enough to take a sequence of finite rank operator to an invertible operator, which is not even compact.